This is part 2 of the video that will make up for the class I missed on Friday last week. Let me say more about drawing the configuration of a chirality center. There are basically two types of drawings that can be used to display a chirality center. One is a wedge type 3D formula, and the other is a Fisher projection formula. Let's first look at the 3D wedge formula. The first drawing, calling it version 1, is a 3D wedge drawing of an alcohol. The chirality center is the carbon attached to the hydroxyl group. The chirality center has a wedge for one of the bonds and a dash for the other bond. The other two bonds are normal line segments in the plane of the drawing. This is the most common type of 3D wedge drawing used for chirality centers. One bond is a dash, the other a wedge, and the remaining two bonds are lines in the plane of the drawing. Version 2 is the same molecule, but oriented a little differently. And there's another difference. Version 2 uses condensed formulas for the ethyl and methyl groups. In version 1, I'm using bond line drawings for the ethyl and methyl groups. The third drawing is drawn a bit differently. Two bonds are wedges and two bonds are dashes. Let's look at an example of a Fisher formula used to draw a molecule with more than one chirality center. Here is the Fisher projection formula for glucose, the well-known simple sugar. Can you find the chirality centers? How many are there? There are 4. 1, 2, 3, 4. Now remember that a Fisher projection formula is a 2D drawing that represents a three-dimensional object. The Fisher formula drawn in 2 dimensions represents a three-dimensional molecule. To its right is the 3D wedge formula that corresponds to the Fisher formula drawn on the left. And the Fisher formula groups at the ends of horizontal line segments point toward the viewer in the 3D formula. So you hit this H and the OH on the horizontal line segment. In the 3D wedge version, there are wedges pointing toward the viewer. That's true for all of the groups attached to the horizontal line segments. They all point toward the viewer. Alright, let's return to the alcohol with one chirality center, for which I had drawn different 3D formulas. Let's apply the Kahn and Gold-Prelog rules to determine the configuration of the chirality center in the alcohol molecule. Alright, proceeding as we did in class previously, we have the following priority ranking of each group attached to the chirality center. The highest priority is the hydroxyl group, number 1. Next, the priority 2 is the ethyl group, and third is the methyl group, and fourth is the hydrogen atom. Note that the way that the structure is drawn, the lowest priority group or atom is hydrogen, and it's shown with a dash bond, and that's convenient. That's really what we want. Let's replace each group of the chirality center by its priority ranking. The OH will be replaced by 1, the ethyl group will be replaced by 2, methyl by the number 3, and hydrogen by number 4. As we examine this, again noting that the lowest priority hydrogen, number 4, points away from you, the viewer. Facing us are groups that are in a circle. The procedure is to find and point to the number 1 group, then move to the number 2, and then finally number 3. Look at the direction that you're moving in. In this case, it's counterclockwise, and that means that it has a configuration of S. So the configuration of our chirality center and our alcohol molecule is S. Okay, next let's consider a ring structure containing a chirality center. At first thought, it would seem that a ring carbon could not even have 4 different groups, a requirement to be a chirality center. Because a ring carbon has 2 substituents and a ring, the ring is really one group, a single carbon chain connecting the carbon atom to itself. Well, one way to look at this is as follows. Let's consider a cyclic compound with a hydroxyl group. It's a 6-membered ring with an OH group. The compound itself is called cyclohexanol. Is the carbon bearing the hydroxyl group a chirality center? To determine this, what you want to do is bisect the ring with a plane passing through the carbon bearing the hydroxyl group, and that plane is perpendicular to the ring. If this is a plane of symmetry, half of the ring is a mirror image of the other half. The molecule is achiral overall, and the carbon atom is not a chirality center. On the other hand, if the plane is not a plane of symmetry, the 2 halves of the ring are different, and the ring carbon is a chirality center. In the example here of the cyclohexanol, the bisecting plane is indeed a plane of symmetry. The carbon bearing the hydroxyl group is not a chirality center. However, consider this molecule. This is a cyclohexanol with a methyl group attached. Alright, we pass a bisecting plane perpendicular to the ring through the carbon bearing the OH group. If you see here, the left half and the right half are no longer mirror images. Thus, this plane is not a plane of symmetry, and thus the carbon in question is really a chirality center. It effectively has 4 different groups: the OH, the hydrogen, this chain part of the ring, and as the third group, and the fourth group is this chain, which is different from the other chain, the chain connecting, or rather having a methyl group. So indeed, this carbon of the ring is a chirality center. All right, with our new understanding of stereoisomers and chirality centers, let's look at something that's similar to things we've done before. If you recall, in Chapter 2, we had examples where one is presented with two structures. The objective is to determine if they are the same compound or isomers. And if they're isomers, what type of isomers are they? In the situation we're going to examine, we're going to be looking at two different molecules. The molecules will have two or more chirality centers. There are three possibilities. They're identical compounds, they're enantiomers, or they are diastereomers. When you're comparing, the first thing you want to do is to make sure that the two molecules, the way they're situated, are as close a match to each other as possible. If they're not, you may have to flip or turn one of them so that like parts of the molecules are in the same relative positions. Next, you're going to compare the configuration of chirality centers. Compare the configuration of corresponding chirality centers of the two molecules. There are three situations. If corresponding chirality centers have identical configurations, the compounds are identical. If the corresponding chirality centers have opposite configurations, the compounds will be enantiomers. If one or more, but not all, chirality centers have opposite configurations, the two molecules will be diastereomers. All right, let's consider this example. We have two molecules. There are three possibilities. They're identical compounds, they're enantiomers, or they're diastereomers. The first thing we want to check is, are their orientations such that they're as close a match as possible? If they're not, we may have to take one and either turn or flip it so that they are as closely matched as possible. In this case, yes, they do match very closely for both. That the top ring carbon has a hydroxyl, the bottom ring carbon has a chlorine, and on the right lower part of the ring we have a methyl attached. So here we go with our comparison. Find the chirality centers in each. All right, this carbon is a chirality center, this carbon is a chirality center, and the bottom carbon here is a chirality center. I hope you all see that. All right, let's compare the configuration of corresponding chirality centers. The top carbon first. We have the OH up and the hydrogen back, and over here we have the same. Both of these chirality centers have identical configurations. All right, let's look at the bottom chirality center. They're identical as well. The remaining third one, you see they're opposite configuration. One on the left has a methyl pointing down, and in the molecule on the right, the methyl points up. And here's our situation. Two of the chirality centers are identical. The third chirality centers, the configurations are opposite. Thus, these two are diastereomers. All right. Thank you for watching the video. Goodbye.